So in the previous ultrasound physics sessions, we did spatial resolution, and we defined what spatial resolution is and the components of spatial resolution, which you have axial resolution and lateral resolution. We went on to define uh, what a pulse is, because it's important for you to know what a pulse is. We talk about spatial pulse length or pulse length. We also talk about the, 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 the pulse period. We talk about the pulse repetition period, the pulse repetition frequency. We define duty factor. What is duty factor? So all those things, you have to know the definition for them. Okay, you have to know the definition for them. And if there's a mathematical formula that describes them, you have to know the mathematical formula. It don't make any sense you go on unless you have those background information. All right, so we moving on now to temporal resolution. And when you see something say temporal, it's usually a time event. And let me see if I can explain what temporal resolution is to you. If you look at films, way back, and you have the films with the little negative, and we talk about the film reel, and we'll put it on something and it spin, and then we see the movies. So each of those little image that you see, each little image is what we would call a frame. So each of those little images is a frame. And then when we put it on and it spin, we talk about the frame per second. Okay, the frame per second. So temporal resolution is basically the frame per second, so to speak, or the time between each frame. And when it's a certain, when you time it a certain way, then you see the images and you see the movie. Okay, so it has to be at a certain speed for you to see the movie, in a regular fashion. So each of those little image would be a frame. When we talking about ultrasound and ultrasound imaging, uh, a frame is, a series of image. Okay, and but let's look at what those image consist of. If you've been following me all along, you'd understand that you send out the ultrasound, the probe sends out the ultrasound beam. The ultrasound beam strikes the tissue and then come back to your probe and you see an image. So when you look at a frame in an ultrasound image, a frame is nothing more than an ultrasound image going to the structure, striking the structure, and coming back to the probe. Okay? And then you're going to hear we talk about scan line. One scan line is just a pulse, one pulse, which travels to the tissue, strike the tissue, and reflect it backward. That's what we call a scan line. So a scan line is nothing more than a transmitted pulse and a reflected pulse. And a series of scan line makes up the frame. So if we could draw that, because as I say, you have to have a clear concept of this. So if we can draw a frame looking like something like this. So each frame consists of a series of scan lines. So these are these little lines, and you must have seen ultrasound depicted. So each frame consists of multiple scan lines. Okay, so if this is a frame, okay, each of these lines, each of these lines in the frame, you see the frame consists of a series of scan lines. So these lines are called scan lines. These scan lines is a transmitted pulse or a transmitted ultrasound wave and a reflected wave. So the ultrasound wave travels to the tissue, strike the tissue, and come back. So each of these scan lines is a transmitted pulse and a reflected pulse. Okay? So each of these scan line. So a series of scan line makes up a frame. So this is one frame. So if you want to define temporal resolution, it is the time from the beginning of the frame to the next frame, or the time from the beginning of one frame to the next frame. Okay? And then an image. To see an image, to get an image in ultrasound, you need a series of lines. That is these lines. But each line is a transmitted and a reflected pulse. So you send out an ultrasound wave to the tissue, and it is reflected back to the ultrasound probe. So each of these lines represent a transmitted pulse and a reflected pulse. And a number of scan lines make up the frame. So each frame is created by a repeated pulse. Okay? So you see that? So each frame is created from repeated pulses that form scan lines. So you have to have those definitions clear. All right. And this is just looking at it. So this is a much neater diagram than mine. So this is a frame. So each frame is made up of these scan line. And a scan line is a transmitted pulse and a reflected pulse. A series of scan line makes up a frame. And, you see the image as a result of that. Okay. So so you can when you look at the frame has a angle. So this has an angle, and it might be 30 degrees, 45 degrees, 60 degrees, or 90 degrees angle, and it's going to contain a series of scan lines. Okay, each scan line is a transmitted pulse and a reflected pulse. All right. So when we talk about temporal resolution, is the ability of the ultrasound system to distinguish between instantaneous events of rapidly moving structures. So basically, if your tissue is moving, then you're gonna have to utilize temporal resolution, okay? Because the faster the moving, the faster the structure is moving, you have to increase your frame rate in order to see that structure clearly. Okay, so high frame rate enhance temporal resolution. So if something is moving very fast, you have to increase the what we call the frame rate. That's the when we talk the number of frame per second, that's a frame rate, the number of frames per second. So a very fast moving structure, you increase the frame rate. And so a high frame rate uh, enhance temporal resolution. Okay, and then when we talk about sweep, it is the movement of the ultrasound beam through an angle, as we showed you before. So each angle, when we talk about a sweep can be 30 degrees. That's an angle. 45 degrees, 60 degrees, 90 degrees. Okay, so if you look in your ultrasound machine, when you're doing study, the sweep speed is usually 50 frames per second. Remember what we said, what a frame is. A frame is nothing more than a series of scan line, and you have an angle that. So the sweep speed. So when you look at is the sweep speed is normally 50 frames per second. So you have 50 of those little frames in each second. So each second, you have 50 of those little frames. And that's what we normally set it at. So if you look at the ultrasound, the face of the ultrasound, so when you look at the face of your ultrasound screen, you should be able to define all the numbers that's there. You're going to see frame rate. You're going to see what we call uh, you're going to have mechanical index there. You're going to have your frame rate along with other things, and you need to be able to define everything that's there. So again, the sweep, when we talk about a sweep, we talk about the movement of the ultrasound beam through an angle, and the angle can vary. And then we talk about the frame per second, which is usually represented FPS, frame per second, and it's usually about 50 frames per second. You can change that, but it's important for you to go back to basics, because this is, if you just understand the basic concept, you can work out everything. So when we say a scan line is a transmitted pulse and a reflected pulse. So the ultrasound wave have to travel to the tissue a certain distance. So it depends on the depth. So when you also have your depth on your screen, and you can set that. So depending on the depth of the tissue, okay, the ultrasound beam is going to travel from the probe to the structure. It's going to strike the structure and kind of reflect it backwards. So you see, it's going to travel twice the distance because it has to travel to the tissue, reflect it from the tissue, and come back to the probe. So it's going to take a certain amount of time to get to the tissue and come back, and it's going to travel a certain distance to and from. You already know the speed of ultrasound in tissues. We talk about that. We repeat that over and over. It is 1540 meters per second. Okay, that's the speed of ultrasound in soft tissue. So you have the distance, and you have the speed. So you can work out the time. You can work out the time that it's going to take the ultrasound beam to travel from the probe to the tissue and come back. You can work out that time. Okay, so you can work out the time for each scan line, because that's what that says. Remember, the transmitted pulse and the reflected pulse is a scan line. So you can work out the time it's going to take to get one scan line. Okay, you can work out the time it's going to take to get one scan line. Okay, all right. So if you have a depth of 15 centimeters, that is, the ultrasound beam have to travel 15 centimeters to the structure and 15 centimeters back to the ultrasound probe. So the total distance that the sound wave is going to travel is 30 centimeters. And we know the speed. The speed of the ultrasound in soft tissue is 1540 meters per second. But because this is centimeters, you have to convert everything to centimeters. So 1540 meters per second is 154,000 centimeters per second. Get all the units straight. And we know that speed is equal to distance over time. So if we want time, time would be distance divided by velocity or speed. Okay? That would give you the time. So the time from the transducer and back would be the distance over the velocity. We say it's going to take 15 centimeters. It's going to travel 15 centimeters to and 15 centimeters back to the ultrasound probe. And then the velocity, getting the units have to be the same, 154,000, the velocity 154,000 centimeters per second. And when you work that out, you get 0.000195 seconds, which is, just move the decimal point 3 points and you get 0.195 milliseconds. So each scan line is going to take 0.195 milliseconds to go and come back. So that's the time for each scan line. So each scan line would take 0.195 milliseconds. Just basic math. Okay? So if we're talking, this is what when we do our regular ultrasound, we use a sweep speed of 50 frames per second. So 50 of those frame in each second. So if you have 50 frame in 1 second, 50 frame in 1 second, each frame is going to take just, so 1 second is 1,000 milliseconds. So you have 50 frames in 1,000 milliseconds. So each frame is going to take 1,000 divided by 2. Each frame is going to take 20 milliseconds. Each frame is going to take 20 milliseconds to be completed. But remember what we said. Each scan line, the time for each scan line is 0.195 milliseconds. So you can find out the number of scan line in each frame. All right, just going back, remember each scan line is going to take 0.195 milliseconds, and each frame is going to take 20 milliseconds. So to find out the number of scan lines in each frame, you divide this 20 by 0.195. So the number of lines, scan lines, that is per frame, would be 20 divided by 0.195, which is 102.6 scan lines per frame, or pulse. Remember, it's a pulse. So that is the number of scan line per frame. Okay. So you have that. Remember the definition for pulse repetition frequency. Remember, so you always have to have these definitions clear. Pulse repetition frequency, it is the number of pulse per second. The number of pulse per second. I just showed you that each frame have 102.6 scan lines. So then, which is a pulse. Each line is a pulse. So the number of pulse per second, if you're talking about a 50 frame per second, so you have 50 of those frame in a second. So it is going to be 50 times the 102.6. So this is the number of scan line, or the number of pulse per second. And this is this is the pulse repetition frequency. Okay, so you can sit down and you can work it out. It is simple math. You just have to have the concept clear. Okay, so this is the number of scan line, or the number of pulse per second. Okay, pulse repetition frequency. Remember, the pulse repetition period is 1 over the pulse repetition frequency. Okay, so let's look at a few things now. So using the example I just gave you, if the scan angle, if the scan angle is if the scan angle is 30 degrees, remember we said that in each frame you have 102.6 scan lines. A scan line is just a transmitted pulse and a reflected pulse. That's what a scan line is, or if you want to call it a pulse. Each scan line is a pulse. So in 30 degrees, if this is 30 degrees, then you have 102.6 lines in 30 degrees. Okay, so for each degree, you just divide 30, 102 into 30. So for each degree, you will have 3.42 lines per degree, right? Because if the total angle is 30 degrees, each degree will contain 30 divided by 102.6. So you get this amount of lines per degree. But if it was 90 degrees now, say this angle is 90 degrees, then each degree would contain the same 90 divided by that. So you'll get, sorry, yeah, 90 divided by that. So it would be much less. It will be much less than over here. Okay. Okay. So for 90 degrees, it will be 102 divided by 90. So each degree would be 1.14 line per degree. So right away you can see that this is a more dense situation. So the smaller the angle, you're going to have more scan lines. So this is a higher temporal resolution. So what you see right away, you can increase the temporal resolution by decreasing the scan angle. Because if you decrease the scan angle, you're going to have more lines per degree. Okay? Okay, so you're going to have more scan line per degree. All right, so if this is 30 and you have 102.6 lines in this 30 degrees, each degree will contain 102.6 divided by 30, so it's 3.42. Whereas if it's 90 degrees, then each degree is 102.6 divided by 90, so it's 1. So yeah, it's less dense. So you can decrease temporal resolution by increasing the scan angle. You can increase temporal resolution by decreasing the scan angle. Okay? All right. So temporal resolution, okay, the line density, the greater the line density, the greater the temporal resolution. So again, you can decrease the line density and it's going to decrease the image quality. If you want to increase the image quality, you can increase the line density, or you can decrease the angle, the scan angle. So decreasing the scan angle will increase your image quality. Okay, you can also increase line density. If you want to increase line density, you can decrease the sweep speed. So if you want to increase the line density and hence increase temporal resolution, you decrease the sweep speed. So you can, if say for instance, if you move from your 50 frames per second and you go to say 25 frames per second, using the same example before. So if you move your sweep speed from 50 to 25, that means you're going to get 25 frames in each second. Every second you're going to get 25 frames because you're decreasing the sweep speed. So you're going to have 25 frames every second. 1 second is 1,000 milliseconds. So each sweep or each frame is 40 milliseconds. So each sweep or each frame is now 40 milliseconds. And using the same thing with same depth of 15, the time is equal to the distance divided by velocity, same velocity. So each scan line is going to take 0.195 milliseconds. And then the number of line per sweep, just like we did before, because each frame is 40 milliseconds. So the number of scan lines per sweep is 0.195. So you see you have much more line or much more pulse per frame. So 201. So you can increase your line density, increase temporal resolution by decreasing sweep speed. You can also increase it by decreasing the scan angle and hence increasing the line density. Okay, so the line density can also increase. You can also increase the line density by decreasing the depth, and we can go through that exercise as well. So if you decrease the depth from say 15 centimeters to to 10 centimeters. So instead of the ultrasound beam traveling 15 centimeters, it's going to travel 10 centimeters to and from. So the total distance travel would be 10 plus 10, so 20, because I have to travel to this tissue and come back. So the total distance travel will be 20 centimeters. The speed remains the same. So if you want to calculate time, it is distance divided by velocity. So you have less distance, 20. So the time for each scan line would be 0.130 milliseconds. And then if you have a sweep speed of 50 frames per second, each frame or each sweep is going to take 20 milliseconds. Okay, so the number of lines per frame or sweep is 20 divided by that. So you see, you get much more line per sweep if you decrease the depth. So you can increase temporal resolution by decreasing the depth or decrease the sweep speed. You can increase temporal resolution by decreasing the depth. We show you how the math works. Or if you decrease the sweep speed, you can also increase temporal resolution by decreasing the scan angle. We went through that mathematic scenario. Okay, so you need to get good concept understanding of these terms and how you can work them out. So again, temporal resolution have to do with time. It has to do with the time between each frame. Okay, remember, a frame is nothing more than a number of scan lines, and a scan line is a transmitted ultrasound and a reflected ultrasound. That's a scan line. A series of scan lines make up a frame or a sweep. Okay, you can, you when you do your ultrasound, you have to have your sweep speed, either 50 frame per second or 100 frame per second. Okay, and as we have shown you, the mathematics, you can increase your temporal resolution by decreasing the sweep speed, decreasing the depth, or decrease the scan angle. M-mode echo have a much greater temporal resolution than two-dimensional echo. When you're doing M-mode echo, you're going to use a frame rate of 1,000 to 3,000 frame per second. Whereas when you're doing regular two-dimensional echo, you use 50 to 100 frame per second. M-mode echo have much greater temporal resolution. Okay. All right. Now we're going to move on to what we call dynamic range. So when you look on your screen, your ultrasound monitor, you're going to see something say DR, or it may say DNR, which is just dynamic range. And what that is, it is the ratio between the largest and the smallest ultrasound signal. The ratio between the largest and the smallest ultrasound signal, and it is usually measured in decibels. So when you see your dynamic range, it's going to be measured in decibel. A large dynamic range is good, small is bad. So when you look at your ultrasound, your two-dimensional ultrasound, you're going to see a series of bright and weak echoes, what we call varying shades of gray. So remember, when it's bright, it is what we call a constructive interference. When it's dark, it is just destructive interference. Okay, so the varying shades of gray is going to look at bright and due to bright and weak echoes. All right. You can increase your dynamic range by increasing the compression. So some of the ultrasound monitors, some of the ultrasound systems, especially the older system, you'll see something say compression. So you can increase the dynamic range by increasing the compression. Not all system is going to have that, but the ones that have it, you can make that change. All right. So that is dynamic range. They probably give you a half of a question on that, so you're not going to get a lot of stuff on that. So when you talk about the high dynamic range, you have more shades of gray, okay? Uh, and you have a low contrast image. A low dynamic range, smaller difference between the shades of gray into high contrast image. So on the machine button, you're going to have the dynamic range. It can be compression or log compression. So all of these things mean the same thing on the machine. The dynamic range, compression, log compression, they basically say the same thing. So, so this is a dynamic range of 35 decibel, and so it's a low dynamic range. So there's not going to be much difference between the bright and the bright and the weaker image, not much difference. Whereas our larger dynamic range, you can see that there's a distinct difference. So for large amplitudes, you can for large amplitudes, you can do increase your compression, the amplitude signal. All right, so the only thing you have to know about dynamic range, it is the range between the large and the low echoes. Okay, and you can adjust it. A large dynamic range is better than a small. All right, now we'll come now to signal to noise ratio. Say on the monitor, you'll see SNR, signal to noise ratio. So the only thing you need to know about this, you need to get more signal to noise. Okay, so the signal is the ultrasound wave being measured, desirable that. So you need, so the greater the signal to noise ratio, the better the image. Okay, you need more signal to noise. Noise is bad. So okay, so you need a greater signal to noise. So a large signal to noise ratio is good. It is also measured in decibel. Ratio higher than 1:1 indicates more signal to noise. You need more signal than noise. That's good. So on the machine, you will see SNR. Okay, we're not going to go into that. And that is how it's measured. It's a logarithmic system. You just need to know that you need more signal to noise. Larger is better. Then when you come to gain now, so you're going to see the gain button on the ultrasound system, and when you look at the monitor, you're going to also see gain. You have overall gain and you have your TGC. Okay, so gain is similar to brightness. It's not the same thing, but it's similar. There's an amplification of the returning signal. You know, so you can manipulate the returning signal and you can amplify that, and then it's going to regulate the strength of the echo. Okay. So say for instance, you're not seeing a structure very well. You can increase the gain to see that structure. All right. So, you know, if you look at this image, I mean, you're seeing most of the structures, but it's not very bright. So you can increase the overall gain. So when you increase the overall gain, it looks brighter. Okay. So you basically amplify the returning signal and regulate this ultrasound. When you look at your TGC, which is your time gain compensation. So these buttons, okay, these TGC buttons, what you do when you manipulate them, okay, you're gonna look at your image, and the area that you have what we call a dropout, or the area that you have a weak signal, you're going to increase the signal in that area. So your TGC which stands for time gain compensation, signal loss uh, from deeper in the tissue. So the structures that are deeper in the tissue. So you image in the heart, and you're looking from the apex to the base of the heart, to the apex down to the atrium. Structures in the atrium may, because of attenuation, because it's deeper into the tissue, you may have loss. You may have signal loss because of attenuation. So you can adjust your TGC just in that area to compensate for the loss due to attenuation. So it's adjustment and compensation at each depth. So at each depth, you can adjust to improve your image quality, or you can improve attenuation at each depth by adjusting the TGC, and it accounts for tissue attenuation. So wherever you have weakening of your ultrasound imaging, you can adjust that area. So if you look here, the left ventricle looks great, but when you come down into the atrium, you have dropout here, you have dropout right there. So all you have to do for this depth, you just increase your TGC. So just for that depth, and you see the atrium fills in well, and the atrial septum fills in well, okay? By just adjusting the TGC, time gain compensation, you can improve. So you need to look at your image and then adjust your TGC accordingly. And these are the buttons, so they look, on the different machine, they're gonna look different. So time gain compensation, and you can adjust for each depth. You can adjust for each depth, okay? All right, so what I'm gonna do is I'm gonna stop here, and you guys need to go over what we can do